Lesson 20 is about dilations, which are like a new type of transformation that we haven't talked about yet. So up until this point, we've only talked about the like rigid transformations, which are ones where the object does not change its size or shape. Rigid transformations are translations, rotations, and reflections. And dilations are considered a non-rigid transformation because they will actually change the size of the original object. So starting with 20.1, we're just going to define dilation. So in the top left corner, the dilation is a non-rigid transformation in which the pre-image is either enlarged as it moves away from or reduced as it moves towards the center of dilation. So it's considered a non-rigid because it does change the size of the object. In a dilation, the side lengths of a figure change proportionally, meaning each side length changes by the same multiple called a scale factor. So what that means is if I have like a triangle and one side doubles, the rest of the sides also double. They're all changing by the same multiple, and we call that multiple a scale factor. Okay, in a dilation, your side lengths will change, and they'll all change proportionally, like we said, and then angles will all remain exactly the same. So, like the angles would not double because then you would go from like having, for example, in like a triangle, the first triangle has 180 degrees, and I tried to double all the angles, then I would run out of degrees that I have for a triangle. So no matter what, of any size, like a triangle would always have 180 degrees, regardless of how big or how small it is. So it's just kind of like one example of why the angles would have to remain the same. So I'm going to look at the kind of dilation on the right side over here first. So usually we'll have one of the figures labeled as the pre-image and one of the figures labeled as the image. We don't hear, so it's not like a huge deal. But the main thing to notice is that between, I'm going to call the blue triangle the pre-image, that's the one we start with, and then the red triangle will be the image, that's one we finish with. So between the pre-image, the blue triangle, and the red triangle, the image, it definitely grows, but the main thing to point out is that the angles don't change. So this is 36 degrees, 81 degrees, 81 degrees, 63 degrees, 63 degrees. So two very different size triangles, but the angles are the same, so it's kind of like keeping the same shape, it's just growing in a proportional way. And then another example of a dilation over here. And dilations don't only have to be where something is becoming bigger. Something can also be like reduced as well. So let's say that, the green triangle is my pre-image. That's the one I start with. And then I'm finishing with the image is the purple triangle. You can see the side lengths are shrinking. Like I'm going from 12 to 4, 12 to 4, 17.1 to 5.7. But all the angle measurements are staying the same. They're both 45, 45, 90 triangles. So that's the important thing to know is that the side lengths will change. The angles will be the same in a dilation. Okay, so for example, identify which figure shows a dilation applied to the pre-image to obtain the image. So with a dilation, you should see a proportional change in the size of the object. So two that we can probably eliminate right away don't really change the size of the object at all. So if we look at the second graph, the one that kind of has like the C's for the pre-image and image, the size of those is exactly the same. It's just like the pre-image is getting shifted right and down to get the image. So since the size is not changing, that's not a dilation. And then it looks like in the fourth graph, we just have a reflection. I don't think that's like the perfect line of reflection, but it's reflecting over a line similar to that. But the size of the object is staying the same, so not a dilation there either. And then it's important to realize that a dilation means that there is like proportional change. So whether it's growing or shrinking, it's doing so in a proportional way. So if we look at the first graph, I don't really see this as growing proportionally because like we're just, to get from the pre-image to the image, we're just like losing a row right here. So it's not necessarily like doubling in size or like shrinking in half. We're just like kind of knocking off a row at the bottom, which is not a proportional change. So it would not be that one. And then if we look at that third graph, I know it's kind of hard to see if it's like changing proportionally because we don't have the lengths of the pre-image and the image, like each side of that pentagon. But it's a perfect pentagon. It looks like it's about like each side length is kind of changing in proportional way. That one is going to be our dilation. So it should be the third graph for our dilation. And then we can move down to 20.2. These ones I just have a couple like kind of cases and information on them, and then I'm actually gonna share the like exploration page in the workbook. So 20.1 is when you're, or sorry, 20.2, excuse me, is when you're dilating lines. So there's two cases. So case one is when you're dilating a line and the center of dilation is on the line. So when that's the case, so a dilation of a a dilation of a line that passes through the center of dilation leaves the line unchanged. So keep that in mind. If we have a point that, or we have a line and the center of dilation is on the line, if we try to dilate the line, we can, but it doesn't actually create any significant change. I'm going to show that exploration after we talk about case two. So case two is when the center of dilation is not on the line. So when the center of dilation is not on a line or line segment, the image will be parallel to the pre-image if the scale factor does not equal 1. So all this information is in your workbook. I'm going to share those just so we can actually see the change happening as opposed to just kind of talking about it. So this is case one when the center of dilation is like on the line exactly. So you can see the line is like line A, the center of dilation is H. So this is like with no dilation right now. As I adjust the scale factor, that's going to incorporate the dilation. But think of a dilation as like, if I just like pull on this line, it's going to continue in the same direction, and lines already go on like forever and ever. So if that's the case, then it's just going to kind of continue to fall on itself. So once I adjust the scale factor, the like red line will be our image. So like with the dilation in it. So if I drag this over, I now have a dilation, but you can see it falls exactly on the line. Like it is the same exact line. And the best way I can think of it is like, if I start with my pre-image and I like hypothetically like grab each end of the line and I just like pull it in the same direction it's already going, it's just going to continue in that same direction. And since lines go on forever, it's just the same exact line. Okay, case two is different though. You will get like a actual different image. So if you scroll down, and this is in your workbook as well for 20.2, so you can play around with it yourself. So in this one, this is when the center of dilation H is not on the line. So right now, I'm gonna actually go back. Okay, so this is the original. EF was the like pre-image. And then as I adjust the scale factor, you'll see the image pop up. So like if I make the scale factor 0.4, you can see that there is a line segment MN. That's going to be the image, and it's smaller than the pre-image. And notice like kind of what the scale factor is. I have like a number that's between 0 and 1. We're going to talk about that in the next section. And then as the scale factor gets bigger, so does my image. And then once I hit a number greater than 1, my image is now bigger. It's like kind of causing my pre-image to grow. I'm going to go back to a scale factor of 1 really quick. Notice with like a scale factor of 1, it is the same exact thing as the pre-image. And that's because if I, like a scale factor is something that's being multiplied in, and if I multiply something by 1, it's staying the same. It's not changing the overall value. And then if I make my scale factor greater than 1, the image becomes bigger than the pre-image. But this change only happens for like lines and line segments when the center of dilation is off the line, because in this case you're like pulling something away from the center of dilation. So as like the scale factor gets bigger, you're pulling it further and further away from that center of dilation. .3 is more on scale factors, and really just like scale factors in relation to any general object. So up at the top, under dilation, the length of a segment in the image is a fixed multiple or factor of the length of the corresponding segment in the pre-image. The fixed multiple of the value, or is the value of the scale factor in the dilation. So that kind of just means that like, if you have one side of a triangle, I keep using triangles as examples, but if you have one side of a triangle that is tripled to get the kind of corresponding side of a triangle in the new figure, that would mean that the scale factor is 3 because it was tripled to go from one side or one kind of segment to the other, and that's just in direct relation to the scale factor. So that doesn't have to mean a ton right now. We're going to take it and apply it, and it's not too bad. Okay, so example 1. Find the scale factor that is multiplied by the preimage EF to get the image KL. So the preimage, that is the one that's in blue, that blue segment, and then the image is the red segment. I will tell you right now, you don't necessarily have to use a formula for this. There is a formula written, but you don't have to. So the scale factor is what do I need to multiply the preimage by to get to the image? And if you're like, okay, I can take 3.5 and I can multiply it by 2 to get to 7, the scale factor is 2. But if you ever forget that, or if it's just like unclear, or if there's more difficult numbers, there is a formula that you can fall back on, and it's this. Okay, so we use K to represent scale factor. So in this formula, the scale factor K is equal to the length of the image divided by the length of the preimage. So we would do K is equal to, remember the image is the second one. So the length of the image in this case is 7. So it'd be 7 over the length of the preimage, which is 3.5. So it'd be 7 divided by 3.5, which 7 divided by 3.5 is 2. So it'd be K, or the scale factor, is equal to 2. So this example was when you have the actual lengths of the segments, like from the preimage and the image. You don't necessarily have to have those lengths. You can have like kind of another set of information. That's what example 2 is. So example 2, you can see still like the blue segment and the red segment, those are considered like our image and our preimage. So we don't have those lengths. We have like other side lengths, or we have distances, but we don't have the length of the image or the preimage. What we do have is we have this distance right here, which H is like the center of dilation, what everything is getting pulled from. So we have that distance from the center of dilation to the preimage. And then we also have the distance from the center of dilation to the image. So that's also enough. So this 5 belongs to like kind of that first half, and then the 10 is all the way across. So if we just have the distance, we can also kind of find the scale factor of how you get from one to the other. And then that formula is right here. So K is equal to the distance of the image to the center of dilation over the distance of the preimage to the center. So for this problem, the K is equal to, the image is 10 units away. That's from the center of dilation H to that red segment. And then the image is, preimage is 5 units away from the center of dilation, so that goes in the denominator. And then same thing, we're just dividing. So 10 divided by 5 is 2, so our scale factor is 2. So that means that if later on, if we were given either of the two segments, the preimage or the image, we could use that scale factor to find the other one. Okay, so moving down to types of dilation. So there's just 2 types basically. The object can get bigger or it can get smaller. So in both of these kind of figures here, EF, it's the same as kind of above. EF is the preimage, the blue segment, and then KL is going to be the image, that's the red segment in each. So one type of dilation, when something grows, it's called enlargement. And you can say like, I don't know, it grows in parentheses or it gets bigger. And then the second type is a reduction. So it is shrinking or getting smaller. So these are kind of like exploration. There's an exploration like slider tool in your workbook if you wanted to play around with these and see how they grow. But if not, or at least for right now, these pictures are good just for the notes. So for an enlargement, keeping in mind that the pre-image is the blue segment and then the image is the red segment. So the image is definitely getting bigger, or it is bigger than the pre-image. Like you can see it's longer. And then if we look at the like reduction side, the pre-image is still that blue segment. It's our like blue is the pre-image for both of these. And then on the reduction side, the image is getting smaller. So there is like a specific thing that causes that, and that thing is the value of the scale factor. So if you look at the scale factor on the enlargement side, so under enlargement, the scale factor is 2 versus under reduction, the scale factor is 0.5. So if we think of scale factor as like something that is being multiplied to get a new value, if I multiply something by 1, it's not changing. So that would be like no dilation. If I'm multiplying something by anything greater than 1, it's going to grow. That's why when we had a scale factor of 2, we had an enlargement. It was growing. If I multiply something by a fraction that's like between 0 and 1, or a decimal for that matter, any number that's between 0 and 1, it's going to shrink. And that's why when the scale factor was 0.5, it was a reduction. Like if I were to take 10 and multiply it by a half, it would shrink down to 5. Or like 9 and multiply it by a third, it would shrink down to 3. So for an enlargement in general is when your scale factor is greater than 1. Okay, so an enlargement, I'm going to throw the word enlargement down here just so it's all together. An enlargement is when the scale factor is greater than 1. It can't be like greater than or equal to, it's specifically greater than 1. And if you're like comfortable, you can just use like the greater than symbol like that. And then for a reduction, when something is shrinking, we can't just say less than 1 because this really doesn't involve negatives at all. So we would have to say between 0 and 1. So reduction is when the scale factor is between 0 and 1. And then if we kind of want to write these as like inequalities, just as like a shortcut instead of like writing out the words, for scale factor greater than 1, we can say when k, because k is the scale factor, and then it's greater than 1. And then for the reduction between 0 and 1, you would write that as when k is less than 1 and greater than 0 with the k in the middle. And you don't necessarily have to do that, it's just kind of like a little shortcut instead of writing out all the words. Okay, so enlargement when the scale factor is greater than 1, reduction, it's shrinking when the scale factor is between 0 and 1, so think like a third or like 0.6 or anything that's between 0 and 1. And then I believe this is the last example. So example 3, in the following figure, segment AB undergoes a dilation to become segment XY. Find the scale factor K and the distance from the center of dilation C to X. That was like pretty wordy, so I apologize. But we need to find 2 things. So first we need to find the scale factor. So first we'll find K. And we can find K by one of 2 ways, depending on what information is given to us. So we have the length of the pre-image AB and the image XY. So we can just use those exact lengths. So that formula that involved the exact lengths, that was like the example 1 from up above. So that was the image divided by the pre-image. And this is a good example of when like it may be kind of difficult to say, okay, what do I need? Because if like segment AB is the pre-image, like we started with AB, we started with the blue one, and then it's going to be reduced down to the image 4. And like, I don't know about you guys, but like, I don't know what would I have to multiply 6.4 by to get to 4? I have no idea. But we can use this little formula to like set it up and find it. So the image, that's the red one, XY. So that'd be 4. And then the pre-image, that's the blue one, AB, so 6.4. I'm gonna go back a little bit because in the directions it doesn't specifically say like pre-image AB, image XY. The wording is a little bit different than we've seen so far, but it says in the following figure, segment AB undergoes a dilation. So AB is where we're starting. And then it undergoes a dilation to become XY. So that's where we're finishing. So that's why AB was the pre-image. And then XY was the image. Okay, so now we have it set up, we can just go ahead and divide. So it would be 4 divided by 6.4, which is 0.625. For something like this, you would not want to round to like 0.6 or 0.63. You just want to write the whole thing out. So the scale factor K is 0.625. And then the second thing that we were asked to find was to find the distance from the center of dilation to X. So like we know this entire distance is 6. We want to find just this distance right here. So from, I guess all the way over, but from like the variable or the point X over to C. Okay, so if we know that the whole, I guess this whole distance is 6, and the image or the pre-image is being dilated by a scale factor of 0.625 to get the image, that same relationship is happening between like the lengths from the pre-image and the image to the center. So what that means is like, so we have this whole distance right here. To shrink down to this distance right here, it's going to be the same scale factor. So to find the distance between X and C, we would take the entire distance 6, so or the distance from the center to the pre-image, and multiply that by the scale factor. So we would do 6 times 0.625. So 6 times 0.625 is 3.75. And then that's the distance from X to C. Okay, so it's just important to know, and you can even kind of like think of these. I know they're not as really drawn as triangles, but it's helpful sometimes to think of it that way. Like if I think of this as a smaller triangle, and then the like bigger one is a bigger one, all the sides of the triangle are going to change by the same value. So to go from, hold on, let me erase some of this. If to go from this side to this side is a scale factor of 0.625, then to go from the like whole long side right there to the shorter side would also be a scale factor of 0.625. So that's why we had to take the long side 6 and multiply by 6.2, or sorry, 0.625 to get the shorter side. 3.75. Okay, so biggest pull from this is just with scale factor, all the sides are being multiplied by the same amount, distances are being multiplied by the same amount, angles and general shapes of the figures or the objects are not.